20 seconds, is that right?
Yes, I'm
Okay.
starting the YouTube.
Where's the mouse for this thing? I got it.
Ready to go. Thank you.
So welcome everyone to this week's installment of Grasp on Robotics. I am Ani Shia and I will be the faculty host for today's talk. I am joined today by two of our wonderful students, Francis Awande and Chris Su, who will be our moderators today. I am thrilled and honored to introduce today's speaker, Dr. Julie Adams from Oregon State University. She is OSU's College of Engineering's Dean's Professor and is the founder of the Human Machine Teaming Laboratory and the Associate Director of Research for OSU's Collaborative Robotics and Intelligent Systems Institute. Dr. Adams is one of the most influential researchers in human machine teaming.
Okay, thank you.
So it is not surprising that she's the recipient of many, many awards. But the one thing I will say, she has the unique distinction of being a recipient of an Army Mad Scientist Award. This is the first time I've ever seen that. I have known Julie since she was a PhD, since I was a PhD student. Since I was a PhD student. So for those of you who are not aware, we have the privilege and honor to call Julie our academic sister, since she is a fellow Graspy. So it is with great pleasure that we welcome you home, Julie.
Thank you.
And look forward to your talk.
Thank you. So the other thing that Ani didn't say, for those of you who happen to be here for the 40th, Regina told me that I was the third female PhD out of the lab. So I'm old, been around for a long time. And I was in the lab when it was in 3401. So it's grown a lot over the years, and it's great to see how the lab continues to grow. So today what I want to talk about is the work that I have focused on pretty much my entire career, which is human-robot interaction. My dissertation was on that. And of course, like most Graspies, I like really hard, challenging problems. And so you'll see that this is one of the harder problems in the field. And really what we're going to focus on is how do we estimate workload of the human while they're doing tasks. Now, I should say that my research really focuses on field domains. So disaster response, now that I live in Oregon, wildland fire response, and a lot of military work. And so some of the common assumptions that you as researchers make, like we're going to have perfect communications or even communications at all, is often a problem for us because we just don't work in those kinds of domains. So why is it not? Hang on. There we go. I'm on. It's always the Zoom thing, right? So what is human machine teaming? What we want to focus on is how do we have humans and machines, mostly robots in my case, work together as a team so that they can achieve tasks in a similar way, and in a similar efficiency and effectiveness as a human-human team. So if you've ever played a team sport, there's lots of things that you do as a team member to understand what your team members are. The team has an overall goal that you're attempting to achieve. And some of the ways that you perceive your teammates will be direct perception, other might be indirect perception. Those are the kinds of things that we focus on in my group in order to be able to have the human and robot team together. We aren't necessarily looking at replacing humans. We want the robots to supplement the humans. And in some cases, they may actually replace them. So one of the key things about these environments, again, is, I mean, even though, sorry, I'm like looking at the screen. You know, even though this environment is clearly in an academic environment, in an indoor environment, you know, we're emulating basically a disaster task of, there's actually a fake pipe bomb right here that you can't see very well. And, how do we go about using humans and robots to detect these things? So, but this is more of the kind of domain that we typically think about, right? Our responders are going to be wearing personal protective gear, so they're restricted in the ways that they can interact with the robot. Now, I want to do a little bit of human factors. I like to say that, I have this tertiary research personality. I do human factors, I do robotics, and I do artificial intelligence. And so this is a human factors aspect. So this graph is a pretty common graph in the human factors world about how workload, which in the human factors world is generally just cognitive workload, is affected by the number of tasks. So what we mean by that is you're going to be in the center here in what we call a normal load when you're doing a number of tasks, but you still have capacity to take on doing more tasks, okay? And the tails of the curve are going to be the ends that you're really concerned about. So the overload situation is one that you often hear a lot about. And that is the case where the human is being asked to do more tasks than they can actually take on and do. And so they become less productive. Now, the underload situation is something that gets less of attention, but it's just as important. And we've seen this in some of the Tesla accidents. The human is out of the loop, right? We've seen this in aircraft incidents. The humans are out of the loop. And so they're underloaded, meaning that they don't have enough tasks, they're not engaging with the system. And so when something goes wrong, they aren't actually able to respond in an appropriate manner and deal with the situation. So we want to be able in our work to understand where the human is, sorry, I keep wanting to point at that, where the human is on the scale automatically by the robot, so that the robot can either start engaging the human differently in order to bring them back towards normal workload, or offload either communications with the human or the tasks to bring the human back into the normal load range in order to impact the overall team's performance. Now, as I mentioned a moment ago, most people equate overall workload with cognitive workload, but that's really only a small piece of workload. So if you're in an office environment and you have somebody trying to take on tasks in an office environment, often that workload is truly cognitive, and that's the primary element. But in our world, that's not the case. There's a lot of physical elements. If you are a wildland firefighter, you are out walking around in mountains, you're carrying stuff, you're picking things up, etc. So there's this physical piece, but there's also the auditory piece. And we know from a bunch of work that we did about, probably about 12 to 13 years ago now, that noise level in an environment actually impacts different types of workload, just the auditory aspect, but also cognitive workload. So that's a factor. And then of course, there's a visual factor. So if you've ever tried to do tracking of multiple objects moving around on a screen, for example, or multiple objects in an environment, it's actually a very complex problem, and it really adds to your workload. That's not necessarily, a lot of people would argue that that may be part of cognitive workload, and some aspects of it are, but you really need to call that piece out separately in many environments. And then there's the speech aspect, right? So we break workload down into these three aspects. And the reason that visual is highlighted in this color is because for the first part of this talk, I'm going to talk about the work we've done to develop the algorithms to do this in real time. And we don't have visual in that particular presentation or in that particular work. We actually have just started getting the algorithms to work the way we want them to for that, because we just got a data set collected this past year that includes eye tracking data. Now, the speech is a lighter color because some of the work of my prior student did not include the speech, but at the end of his dissertation, we had an undergraduate honor student who actually developed the speech algorithm component that came in at the end. So this is a high-level system architecture for our adaptive system. And one of the key caveats here is that we have to know what tasks the human's doing. And so for our workload models, we use a tool called Imprint Pro. It's from the Army. And this tool allows us to model underload, overload, and normal load. So not both, it's three. Different ways that a series of tasks can be done. So for this first half of this talk, we are assuming we know what tasks the human is supposed to be doing because we're doing controlled laboratory studies. And then a key aspect here is our algorithm, which I'll talk a little bit about. And then from that, we want to be able to have the robot adapt. So what do I mean by that? In our case, we assume we have a mission plan and that there's an allocation of tasks between the entities in the team in order to be able to achieve that mission plan. So if the robot is able to determine that the human is busy, let's say the human is triaging somebody who needs immediate care and the human is very busy, but the robot is realizing that another important task needs to be done that was previously assigned to the human. Then if the robot is able to detect that the human's workload is too high, the robot can figure out how to reallocate that task. Is that a task that the robot can take on? Can the robot give it to another robot? Can the robot give it to another human in order to achieve it? Similarly, we want the robot to be able to adapt its interaction with the human. So if the robot is using, say, a visual mode, and that human is doing that triage task, then the human probably can't use a visual mode to communicate with the robot. And so the robot has to decide, first of all, do I even communicate to the human right now? Or do I postpone? Or do I have to, this information is important enough, I need to communicate it to someone else instead of this particular human? And if I'm going to communicate to the human, how do I do that? Do I do it in an auditory way, a verbal way, something of that nature? So how do we adapt? And then another piece that my student did right at the end was doing some performance prediction and trying to look at how is the human's workload going to change in the near term in order to be able to figure out which adaptations to do, right? And I'll talk a little bit more about that. That's preliminary stuff. So because we are in these natural environments, we use wearable sensors. And we have to have metrics that are going to work in those environments. So we deal a lot with physiological metrics, such as heart rate variability. You can see noise level, which is really just a decibel meter. And then we have our speech aspects. I crossed out EMG here because while we have the data, we haven't incorporated it into the work that's presented here yet. And then most recently, like I said, we've got the eye tracking data that we're starting to incorporate. So we take these signals and we have to do some signal processing on them to smooth them a bit, but we have to be careful not to over smooth them, or we normalize everything to a point where we can't get the information we need. And we do feature extraction, and we take that current task information and feed that into machine learning algorithms. So we have a separate machine learning process for each of the workload components. So you end up with a separate model for each workload component, which is going to give you an estimate for cognitive workload, visual workload, et cetera. Now, in Jameson's work, my student Jameson, I mentioned we didn't have the visual, and then later on, in the early part of his work, we didn't have the speech. So for both of those, we were actually using estimates from the Imprint Pro modeling, but at the end of his work, we did have the speech component integrated. So once we have those estimates, we can then combine them through a function to get our overall workload estimate. And we can look at the ways that they contribute in order to figure out how to adapt. So I mentioned wanting to adapt like the communication. So understanding which one of those components is overloaded is really critical in order for the robot to be able to determine how to adapt the interaction, right? So if the human's visual load is very high and their physical load is very high because they're doing things, then you don't want to use, for example, a little text message on a wearable device. You want to use that auditory interaction. So as part of Jameson's work, we took data from a peer-based evaluation. This is actually a study done by my first PhD student on this project, Caroline Harriet. And we did civil support team tasks, going around looking for suspicious objects, doing different types of sampling of dry items and wet items, things of that nature, very typical tasks. And in fact, the person who used to be the captain of the Nashville bomb squad happened to be the special forces team lead for Vanderbilt police at the time. And I said to him, I need you to come check this out, or the department head's not going to approve me doing this in our building. And he came over and I'm showing him what I've done. And he's like, I've trained you well. And he was so thrilled. He's like, can I bring my team over? Because he hadn't been at Vanderbilt very long and he just started up this team. And he's like, can I bring my team over and do some training with them? I'm like, sure, go right ahead. So, it was great because we actually had some good ecological validity, which is usually a concern in human subject study. Now, for Jameson's work, we wanted to do something that was more supervisory based. So we needed to find something that was relevant So we looked around and we ended up settling on NASA's multiple attribute battery test, MATB. I got the acronym wrong. Multiple attribute test something, battery, I think. And this particular system, you can see here, is typically a single screen, has multiple tasks in different sections here. We focused on the 4 tasks right here. So this task here, you have a remotely piloted vehicle, and you are trying to keep that vehicle tracked in the center square, typically using just a joystick, right? Here you have a systems task where you're trying to keep these meters in the center. There's various things you have to do. You have the fuel task where you're trying to keep all these fuel tanks full, and fuel is moving between them, and there's different errors that you have to respond to. And in the original MATB, you just had to do some communication tasks where you're just changing things, but we modified that in order to have an auditory and speech component. And so we made it such that there was communications that were occurring, and the human had to be able to decipher which ones applied to them, make the change, and then report back that they had made the change. So Jameson's initial work used the system with all of these on the same screen, and we used that to create the initial algorithm and did a bunch of post-hoc analysis to validate the algorithm. So we validated it across these different human-robot interaction roles. We validated it across different tests and across individual differences, and we got very good results. Obviously it takes a little bit of time to get the algorithms right, but once we got the algorithms right, we get very good results. Now, the next step for Jameson was we wanted to be able to do these estimates in real time, because if we're going to get to being able to do adaptations, we have to be able to do these estimates reliably in real time. So we took that NASA MATB and we split it, each of the tasks, into different screens, and you can see the actual environment here. The idea being that the human could do these 2 tasks without moving and could potentially do these 2 tasks without moving, but there had to be an aspect of moving around, okay? And so again, here we're trying to change the different levels of workload. So we intentionally design the experiment so there's periods of time in which you're in an underload state, then you're going to, say, an overload state, then maybe back to an underload state into a normal state. So we have these sequences, and our evaluations are 45 minutes long. So we want not only to have the period of that workload to be long enough to have good data for the sensors to respond, because you do, for example, with heart rate variability, need about 30 seconds worth of data in order to have a valid data point. But we also want to get the trajectories or the magnitude change between the workload changes so that we're able to identify those changes in workload in real time. So with this evaluation, again, we used our wearable metrics, okay? We did collect speech in that particular one, and we did use the speech estimator model for that instead of the Imprint Pro model. We also do what's called in situ workload probes. So every 7.5 minutes, we ask the participant to rate each of their workload components on a Likert scale. And the reason we do that is because we need to have some idea of what they perceive their workload to be in order to have an idea of how well our system is working. And subjective workloads, I'm not a huge, subjective metrics, sorry, I'm not a huge fan of, because they often tend to be biased based upon personal perspective. But this is one way to get enough data points to help verify that over time. And then we use NASA task load index, which isn't very valid after 45 minutes and you've changed somebody's workload 6 or 7 times. We also, as part of this study, captured EMG data with the MIOs that we have just started to integrate now into our models to help with physical workload on those tasks. So one of our hypotheses for this study was that we wanted the estimates to be within 1 standard deviation of the Imprint Pro models. And so we mostly supported that. We did really well across the 3 components that we assessed: auditory, cognitive, and physical. And sorry, I was thinking speech was in this, but it's actually the adaptive one. And then overall, so we did really well in the underload and normal load situation in comparison to the Imprint model. For the overload situation, however, we only did well for auditory. We were outside of that range for the cognitive, physical, and overall. And for some of this, the physical, there's not a lot of physical interaction in that particular study. So that's part of the criteria for this. Now, the other hypothesis was that we wanted our real-time estimates to be positively and significantly correlated with the corresponding imprint pro models. So what you're seeing here is the dotted line is actually the data for each of the individual components and overall workload. And then the solid line is the model. And so this is a good example of one sequence. So this is overload, underload, overload, normal load, underload, normal load, overload of, and you can see here, you can see this is overload, normal, underload, going back up, and then normal loads kind of in here in the middle, right? But you see very good correlation there. So, all the correlations for the different data sets that we had were positive and significant. So that's great because it actually means things are working the way we would expect them to. So the other piece of this, the last piece of Jameson's dissertation, was to do a small study that looked at how can we do the adaptation, right? And we did that within the same context, that same MAP-B separated with the 4 screens. And, there's some caveats here. I mean, we were doing this rushed because he needed to graduate, he had a job. And so, some of our ideas of adapting the autonomy while they worked and the task was completed more efficiently and everything, the human didn't realize that the autonomy was taking over, even though we were giving them some indicators. So, for example, if the human, let's see if I can get back here. Whoops. If the human were over here doing a task and the system determined that their workload was high, they were busy maintaining that vehicle in the center, they couldn't come deal with the resource management task, and the system took over and did that, even though we provided the human with some indicators, the human saw them but didn't remember them and didn't even realize the task was being done autonomously for them. So overall, the team performed better, but the human wasn't aware. And so that is a concern for us. And we also did adapt the interactions as well, and the way that the system communicated. So we got, good indicators of things that we were looking for. Whoops. Oh, I did go too far. Hang on. Good indicators of the autonomy adaptation that we were looking for, which was great, but we weren't quite happy with that study. So what we've been focusing on for the last year has been a little bit different, and we have kind of stepped back from the adaptation right now until we get this next study done, and then we'll be moving on to that. I'll talk about that in a moment. The last piece of Jameson's work was this performance prediction piece that I was talking about. So he did a very simple prediction into the next 15, 20 seconds, not quite as long as we wanted. And so that's an important piece there as well. And again, I want to make sure that it's very clear, all of this work required knowing what the task was in order to get the prediction. So, visual workload, I mentioned, we collected data in the last year. And in fact, no, it's the other one that's being presented right now by one of my students. So just last week, one of my students who's actually presenting on something else that I'll talk about in a moment, right now at a conference, told me we were finally getting some good results for the visual workload. So we had an REU student over the summer who started working on it, got some reasonable results, and we've been refining that using eye tracking metrics. The other piece here for the domains I'm talking about, right, like wildland fire response, there's different aspects of physical workload that really have to be understood. And with the metrics that we use, and I can tell you this because I just did the analysis yesterday in my hotel room, it's clear that our metrics for physical workload, because they're heart rate, respiration rate, and then some body movements, that the heart rate and respiration rate are impacted by fatigue and stress. And that's clear from the data set I'm going to present in a moment, which I didn't tell you because DARPA hasn't approved me to tell you. That's probably on video. But the piece that Josh is presenting probably right about now is this piece of how do we break the physical workload down. So there's gross movement, like moving around like this. There's fine movement, like trying to get into a precise precision or precise location. And then there's the tactile piece. So, you're typing or you're pushing a button. That's important feedback that you need to know. And so what Josh is presenting right now is work that we've done attempting to identify those components. And in the study we did, we used a variant of that MAP-B study again. So we're lacking some of the interactions for physical that we wanted, but we've got that data and we're getting ready to run another study that will address that. So Jameson's graduated, he's off at RIT being an awesome professor there. And so we have all these other things that we still need to do. By the way, I've been working on this for 15 years and we're still not there yet. But the first piece is task recognition. So one of my students is actually presenting also right about now. He's presenting right before Josh at the same conference on how do we do visual component task recognition. So again, we break down into those different components in order to understand what's contributing to the task so that we can try to identify it. We've done some prior work in medical domains, but that is a structured environment where we can use cameras in the environment and such. So we have to look at different ways of doing that. So that student's going to be graduating this academic year, and we're starting to make good progress there. And we need that in order to be able to know how to do the workload estimations and do the autonomy, right? So we want to kind of move away from these workload models and actually be able to recognize the tasks in real time. So the other piece that I have a student working on is the performance prediction and trying to look beyond what Jameson did, so into the next 5 minutes or so. Because if the operator is overloaded right now, then they may not be overloaded in 5 minutes when they need to do this important task. But we have to be able to predict what's going to happen based upon the mission plan, what the operator is doing. Maybe the task is different than we thought we planned for, right? So if you're triaging a patient or victim, and that victim requires immediate care, well, that human is going to attend to that victim no matter how long it takes. So that may conflict with a task that needed to be done in 5 minutes. And so we have to be able to predict that. So I have another student who's just starting that research. And then the other piece that is particularly true in disaster response, and any first responder will tell you that every event is different and you cannot plan or even come up with a mission plan for every single event. There's always something different. So we have to be able to not only identify tasks, but also do the algorithm assessment or estimates with unseen tasks. So I have another student, Josh, who is actually focused on how do we bring in things like few shot learning, zero shot learning in order to be able to estimate the workload components and overall workload for these previously unseen tasks. And then finally, sorry, not finally, we're of course doing the adaptation. Our next study is not going to focus on that because we need to get Prakash done in time. And these are large studies. These are 54 participants. It's a 2-day study and each session is 2 hours. So if you've ever done human subject studies, that's really intense. So the next study for Josh and Mark's dissertations, final dissertations, will have the adaptivity in it. And then we're trying to move to scenarios where we also have multiple robots that are working with the human. So that's kind of the background. And what I want to do next, and I'm trying to watch the time because like I said earlier, this could be a 10-hour talk or it could be a 20-minute talk. I want to talk about the DARPA offset program and how we use this algorithm to collect a very unique data set. So DARPA offset is a swarm-based program, or was, it's done now. And I was on one of the 2 integrator teams as a co-PI. So I was on the Raytheon BBN team with Smart Information Flow Technologies, or SIFT, as we call them. And I was the only academic co-PI in the integrator teams. And so this program was designed by the end of the program to deploy up to 250 ground and aerial vehicles in an urban environment to do standard kind of 3-phase missions for the military. And so what we want to look at here, and a lot of my research over the years, because we haven't really solved human robot interaction with multi-robot systems. So I decided we have to move to swarms, right? Because you just make things harder. That's how you keep your career going. As you find another harder problem to get funding for. So how do we take that teaming aspect? And here what we want is we want those agents that are biologically inspired in most cases. They're simple agents. They're not the robots many of you are working with. And how do we get them to coordinate and cooperate with humans while also exhibiting autonomous decision-making. And in this program, I should say there's a couple of caveats. So first, your robots are very autonomous. You're never doing any teleoperation. You don't have the capacity to do that. Second, these are very simple robots. You don't have the funds, right? And these captives are located, a captive is an urban training environment for the Army, are located in places where you don't even mostly have cellular coverage. And if you try to use Wi-Fi, it doesn't work. In fact, someone, I don't remember your name right here in the middle. Yes, so he mentioned being at Fort Benning at one of the field exercises. And at that field exercise, we were still trying to use Wi-Fi to communicate with the robots, and it worked horribly. So we finally, DARPA didn't intend to have to support buying a communication system for the teams, but they had to. So our team actually bought an LTE base station. And the problem with LTE is its line of sight. So if your ground robots are between buildings, you've lost your communication. If your robots go into a building, you've lost your communications. If your unmanned aerial vehicles fly down into the built environment, you've lost your communications. So, these are things that most people don't think about when thinking about how we design robots. So our last field exercise actually ended a year ago today, November 18th of last year, and it was at Fort Campbell in the Cassidy Cactive. You can see this built environment that I was talking about. In this particular cactive, all the buildings are the same color. You have variable buildings. So this is the mosque, there's a church. We have a 5-story city building, there's houses, there's shops, there's warehouses and gas stations. There's all kinds of buildings. And a particularly challenging thing is you can't see it very well, but this building, the step up to get into that building is about this high. Our robots are this high. They can't very easily get into that building, the ground robots. So you're trying to get UAVs into that building. And so when you are outdoors, you're flying using GPS, but then you've got to switch over to like a ROS controlled system in order to be able to function indoors. The other thing is that I mentioned previously, to go back, that the goal of this program was to really scale the robots. Sorry, something just got in my eye. And so you see this April tag here. And so we weren't supposed to focus on developing sensor capabilities. Instead, the artifacts in the environment to play the scenario were embedded into April tags. And this is one of the very first field exercises. So it's a simple April tag. However, by the last field exercise, you often had April tags that were embedded into a single April tag. We had something like, 10,000 different April tag identifiers. Some of them were not very meaningful, like this is building 1. And then we also had 2 instances of April tags, one where the April tags would physically move during the event, and then also April tags that were on displays where they would change. So this display was stationary, but it would change. These April tags were all over the place. They were on the outsides of buildings, insides of buildings, on top of buildings, on the ground. In this case, this is a 3-dimensional one. You can't really see it well in this picture, but on all 4 sides, there's April tags and then on top. And in this particular case, this happened to be the high value target at this particular exercise, but the only way you knew that was if you could see the top. And at that point, our UAVs were not flying indoors. So we were never going to get the high value target in this particular case, but we came the closest. So this is also the area, right? So this is where we can put our vehicles to launch them. And DARPA actually wanted them to launch right here, but we had to have a larger space. And then our commander is in this building here, and we call it a near field position, meaning that they're not out with line of sight to the robots, they're actually further away. And then this entire area was within play. Okay. So our swarm was the heterogeneous swarm of the 2 teams. You might be saying, oh, 3DR solos, right? They were cheap, $200. And let me tell you, they are the best vehicles. They can fly into sides of buildings, start to fall and recover. They can fly into power lines and recover. And yes, there's power lines in these environments. So if you look at this is our most expensive robot, right? And that includes off the shelf, just buying the robot, but also the sensors. One of the most expensive sensors we had was the RealSense. You know, our LiDAR here is the $100 LiDAR. So you are dealing with, you know, noisy sensors in many cases. You've got to be outdoors and indoors. So you're like, well, RealSenses don't work outdoors. So we had filters that had to be literally rubber banded onto the cameras. And then the other thing for identifying the April tag, so here you can see Solo doing this. We use $20 pie cams, right? So very simple technologies to do this. So our commander uses an immersive interface that we call i3. It's the Vive headset. And part of the program, we were having this conversation yesterday amongst us. So partly the program manager wanted an immersive interface, but also in this environment, you really can't just use a top level view or God's eye view. You have to be able, when you're trying to set the point of how close a robot should get to this IED, okay, and this lighter area is representing kind of the range. And some of these April tags are active. So they have a Raspberry Pi with a Bluetooth beacon. The robots have a Bluetooth beacon. And depending upon what the artifact is, you have to respond appropriately and do that autonomously. So the human's not controlling that at all. But you want to be able to get that robot, you want a goal point very close to this IED so that you can neutralize it, but not get your robot killed, right? So having that ability to get into the environment was really critical for doing that. So the operator is just using the standard hand controllers. There's also a chest tracker, and I'll talk about that in a moment. Magenta circle is just representing everything inside that circle is what the operator sees. So these are taken from the monitor. Oh, sorry, I didn't mean to poke I did the laser at the screen down here. So I mentioned this, you know, every artifact we see is a different thing. And when you've got 10,000 of them, you can't display them all, right? It creates too much clutter. So we actually have this one on because this is just a meaningless artifact that we typically filtered out, but we turned it on for purposes of this, right? So you have IEDs, you have adversaries that can shoot you, right? You have all kinds of things. In fact, in the final field exercise, there were some adversarial artifacts in which you had to simultaneously get multiple vehicles to interact with that artifact at the same time. Exceptionally hard. And then here, we actually are deploying a mission plan. So we use two ways to task the robots. Mission plans were a common way. The other way is high-level tasking or tactics. And the idea is sort of like a playbook. You have these predefined things that you can do, like surveil a building. And by default, the parameters are, if you're doing this with UAVs, that you need to have 4 UAVs with a forward-facing camera, and they're automatically assigned 1 to each side of the building. And then the 5th one has a downward-facing camera and is looking at the roof. Okay, so you have these predefined tactics that the operator can select, and the operator can say, okay, system, just identify the robots to assign to this, or in some cases, the human would have to select the specific robots. In the case of the mission plan, the system automatically allocates the robots, and in this particular mission plan, this is the start of a mission. The first phase is simply to send out every robot you can to different buildings along around the captive in order to do those building surveillance tasks. So the color bulbs here mean which tactics the vehicles are assigned to. You also are going to have some ability to identify where your tactics are deployed to. So we have a tactic glyph that typically goes out wherever the point is. In this particular case, we're trying to look at a particular object right here on the street. So it's a surveil object. And when you kind of point at it, which is what this is from the hand controller, you get the pop-up so that you can see what's going on. We also have a heads-up display. So our fixed wings were actually from Hopkins APL. And so we didn't actually control them. They would deploy them. And then we have our rotary vehicles. So we had 65 of them. We had 6 of them that were out of communication and 45 of them that have been tasked. And then here we had 16 ground robots, 3 that were out of communication. The beacon on the chest was used to look up or bring up kind of billboards on the side that would provide you information. So, in this particular case, we've got how many, adversarial agents of a particular type have we found? Have we found a piece of information about the high value target? So typically these were 3-phase missions. The first phase of the mission is to go out and just gather all the intelligence you can, hopefully find information about the high value target. Phase 2 is to try to locate that high value target based upon the information you've gathered. And then phase 3 is to go confine the high value target. So this project is ITAR, so it kind of changed what my original contributions were supposed to be. And that's why I said earlier, we didn't intend to take our workload estimation algorithm out into the field for this. And we finally decided on the last field exercise that we should do this. So, and this is not typical, but we have team members as our human subjects in this case, because it does require some training. So we had 2 CCAS team members, and CCAS is the name of our team, who participated as the swarm commanders. And swarm commander 1 did all the field exercises. There were technically 7 of them because we started with 0, not 6. And then the second swarm commander did FX3 and then FX6. And we tried to split the number of hours of swarm commander between them and the number of hours of data that we would get. This field exercise was 3 weeks long. We work in a tent in temperatures from 20 to 70. It rained inside the tent. I can tell you more about that later. Not good when you have, 150 vehicles. The other thing that I should say, by the way, is I mentioned that this program was intended to deploy 250 vehicles. 2.5 months before our final field exercise, there was a fire at BBN that took out every single battery we had, took out half of our UAVs. And if you remember what it was like last year, supply chain issues everywhere. So we literally were getting replacements for things while we were at the field exercise, and we were never able to actually replace all of our vehicles. We went to the field exercise with 150 vehicles total. This is not going down. There we go. This is an eye chart, but that's okay. So even though it was 3 weeks, we only did data collection starting from later in the field exercise, because you spend the first week and a half just getting everything set up and just testing things out. And so the 11th was supposed to be the first day of data collection, but it rained and we ended up being in the hotel using the simulator. So another piece of this is that BBN took AirSim from Microsoft and modified it to represent our swarm. They've sent some things back to Microsoft, but a lot of what we put into the system we can't share publicly. And so that allowed us to do live virtual deployment. So what you're seeing here are the ground vehicles, how many hardware vehicles we had and how many virtual vehicles we had for both ground and aerial, and then the total. This day right here was exceptionally challenging. If you've ever tried to fly UAVs in 29-mile-an-hour winds, I can tell you solos just drop from the sky. So here, the reason you see so many numbers is that we started out with hardware, then we had to go to software for various reasons. And then the gray here represents which shifts Swarm Commander 2 did. So here's the setup for the Swarm Commander. So we're inside of a building. Basically, it's the laptop and the VR equipment. We are close enough to the launch zone that the Swarm Commander can hear vehicles taking off and coming back, but that's about it for external perceptions. This is my setup here, and you can see it's much more than his. So you can't see everything, but he's wearing the bio harness. He has 2 myos on, 1 on each hand. He has a microphone on, and then we have the noise meter right here to collect all of our data. This is the machine that's collecting all of the data off of the sensors, my note-taking machine, and then of course my monitor. And I do not recommend sitting in front of a monitor watching somebody in VR, especially this particular operator, for 3 hours. You stand up a little queasy. So this is just showing what I was talking about before, the different metrics that we use. And we try to use multiple metrics for each of the components in order to deal with some of those issues, like how does stress and fatigue impact the workload components. And I should also say, sorry, I went to update these yesterday because there's stuff on here that I don't really want to present, but then I remembered this right here, and I can't change them without DARPA's approval. So I'm going to just tell you to ignore some things. What we're going to talk about is the estimated overall workload. And what I mean by that is that during what's the next slide? Yes, during the field exercise, if we were green, then we were collecting the metrics through the sensors. We had some problems with speech at the beginning, and we don't know why this didn't record here. For auditory, we had a problem with the noise meter, and some of the shifts, it would record the whole shift, or some of the shifts it would record partially. It was a brand new one, and there was default setting. So that should actually be a light green, because we did some work there to actually use that instead of the model. And then for visual, we didn't have any data, so we had to use the model. So again, looking at the middle here, what we care about is that overload and underload, and how much were they in that normal load state, right? So for us, overload based on imprint is greater than 60 on a scale of 0 to 100, okay? And underload is less than 25. So if you look at these means, wow, things look great. We're always in normal load, right? If you look at the min and maxes, well, we never seem to hit underload, but 8 times we end up in the overload. We have at least some data points, okay, in overload. That's great, but this is across the whole ship, so it doesn't really tell us anything. So one of the next things we did was we looked at, for every single data point, and you can see that there's almost, there's over 12,000 data points. We classified them as overload, underload, and normal load. And I already told you that there's no underload, so you can see across these shifts, we had 11,500 almost points that are normal load, which is pretty astounding, because prior to this, there's not been any data of this nature collected for a single human working with this many robots. It's typically done in simulation with a God's eye view and perfect systems, right? So this is a really important finding, because people have said it's impossible. And we knew qualitatively over the prior 5 years or 4 years of the program that we were doing this, right? But we needed the evidence to do that. And then, of course, we had, this small amount of overload across all the points. Please ignore the green line here and the blue line here. This is part of what I wanted to get rid of, but then realized I couldn't. Focus on the orange line. The red line represents our 60 threshold for overload. The blue line represents our underload. And then this line here represents another important aspect. So on November 16th, this is the day that all the distinguished visitors come. We had the largest contingent. There's 4-star generals. There's, the head of DARPA, very important people. It's very stressful. And they were observing us for the first 30 minutes. We put out 150 vehicles. And we put out 91 vehicles that day. Sorry, it was a different day. The next day we put out 150. Put out 91 vehicles. And what we wanted was we wanted to use the mission plan to get all those vehicles up in the air and out over the captive, and the ground robots out into the captive simultaneously, because you've got to give them a show, right? And we want to keep that tempo up, right? So we want to keep making sure that all those vehicles are up. So once the mission plan is done, the swarm commander is actually issuing individual tactics for numbers of vehicles and just getting them out, right? And of course, UAVs, as probably most of you know, the batteries don't last very long. So we're not going to make it the whole 30 minutes that we're being observed. And it was really 35 minutes. So this is when they left. So we had a point where if a ground robot was neutralized, they had to go find the medic. Of course, we had to find the medic first, but we typically did. And if a UAV was neutralized, then the UAV just automatically returned to the launch zone. And then at approximately, probably around 10:18, we had a mobile medic that walked through the launch zone to revive all of our UAVs so that we could launch them again. So what's really interesting here is we do see that the orange line goes above the overload threshold frequently, but it's not all the time, right? And this point here is about 73, I think it was. And that's our highest point, which is actually bad, but it's not horrible. And then the other key takeaway is after we're done with that, when we start ramping back down, right? And not having to be such a high tempo for the operator, we're actually reducing the operator's physical, or sorry, I don't want to use the word physical, the robots, the humans' actual tasking demands, that we see the overall workload and the components come back down. And yeah, there's still some times here where they hit an overload, but it's a lot less frequent. So I've actually spent a lot of time looking at the log files and looking at all my notes and everything. And I can actually identify for each of these points where there's overload exactly what was going on. That the person was doing a tactic specification, that they were trying to identify why UAVs were hovering over the launch zone because they were blocked and couldn't plan their path, etc. Let's skip that one in lieu of time. So the takeaway here is that, for almost 92% of our data points, the operator was in normal load. The first time that anybody has actually been able to show that this can be done. And our largest swarm was 140 vehicles. After the solos dropping out of the sky, we lost about 10, so we were down 10, unfortunately. And then for our overload classifications, we end up with 15.8% are classified. 15.8% of the overload classifications occurred during that distinguished visitor observation shift. So this confirms our qualitative observations and is the first known data set of this nature. I want to thank my students and my collaborators who've worked on this and our research sponsors, but I also have to thank Raytheon and SIFT and of course DARPA. This is a very unique program and exciting work. So, thank you.
Julie. So let me reintroduce our student panelists. We have Francis Owande and Chris Sue. If you're joining us via Zoom, please submit your questions using the Q&A button at the bottom of your screen. And these will be answered we will be monitoring our Zoom. And then people who are in the auditorium, feel free to raise your hand.
Are these guys monitoring the Zoom? Yeah. Okay.
Thank you, Julie, for the talk. It's great to see that so much progress has been made on the offset project in the last 3 years. Because when I was there, it was very
mess.
hard. Yeah. So yeah,
Yeah.
it was a mess. So I have a question about the metrics for workload. So I think it's a calling for a lot of roboticists that we want to free people from hard labors, from the boring and repetitive work, so they can do more creative works. But how do you measure creativity in their workload? So the thing is, so we can use self-reported data, but like you said, they have a lot of biases. So is there any objective way of measuring how creative their work is?
So what do you mean by creative? Can you clarify that a bit?
Yeah. So for example, I am on the say the product line of food processing. So for example, if I'm doing deboning of the chicken, right, then me using my hand or tools to keep separating the chicken meat from the bones.
So what are the unique ways that you do it as opposed to someone else?
Yes, exactly. Yeah.
Okay. So I think, if we're just looking at workload, I think we could go as far as trying to analyze what are the types of tactics they're using. When do they use those tactics? And we saw this during the last field exercise. So I mentioned that artifact that needed to have multiple vehicles simultaneously interact with it. The swarm commander's initial decision was to try to use the ground robots, but where the artifact was kind of up against something like this wall right here. And the ground robots just weren't reliable enough and precise enough to get where they needed them to simultaneously. Like they kept killing off robots left and right, trying to do it. So then, much to the chagrin of our BBN folks, they decided they were going to use the UAVs to do it. And using the UAVs, they were able to do it. And so there were very unique ways that both of them took to try to do that. And I think in order to identify that kind of thing, you're going to require a different type of analysis than what I just demonstrated. It really requires kind of looking at, so in our case, I should say, aside from the log files that are generated by the system, we also record all the videos of the human operator. And so that would require a lot of work going back and looking at the nuances between the operators and how they went about doing those tasks in that case. I think in the kind of deboning situation you're talking about, that's where you could potentially use some wearable sensors. There's some new sensors that I just saw something on the plane actually coming here, which uses the Aura ring and a wristband to be able to get the hand movements. And so for something like the deboning, you probably need to have that kind of data in order to be able to get that nuance of how the different people would, debone the chicken. You're welcome.
We have a question online.
Sure.
Dr. Figueroa asks, has a question regarding the machine learning component in the workload estimation approach. She says, do you learn an estimation model for each human subject, or do you gather data from a corpus of subjects and learn relevant features to predict?
Yep.
How do you deal with the variability of the vital signal across subjects? For example, younger adults may have a different normal heart rate than speech and older adults.
Yep. That's a great question, and there's lots of different ways to approach that. So each of our individual workload components have a separate machine learning approach. And so you can tailor that in that way for the particular type of thing, particular component that you're trying to assess. So that's one small piece of the puzzle. The other piece of the puzzle is exactly what was referred to there of, do you learn individual models, or do you learn, I'll call them gross models with everybody's data? We've done both. And with the work that Jameson did, and it was, I think our average age was somewhere in the late 20s, early 30s. So convenience participants, younger participants in this context. We were able to demonstrate that you could put all the data together and do a leave one out type of testing, and that we could generalize these results across the different workload levels. However, while we get very good results with that, we get much better results when we train on the individual. And a key caveat of the environments in which we work, that I work in and my lab works in, is we want to be in environments where the human is going to train with the robot, so that we can use that training data, that training time period, to train the robot and the models, so that when we go out into the real environment, we have pre-trained models that we can apply. So those are caveats. If you're trying to go into a different environment where you're not having that ability for the human and robot to do their physical training together, it's a completely different problem. Hopefully that answers the question. Yes.
Hi, thank you for the talk. It was excellent. I have a question about the instances of overload that were not caused by the distinguished visitors. Could you go into the reasons that those happened, and what sort of systems you would implement either through autonomy or feedback?
So let me clarify that the instances of workload were not caused by the distinguished visitors. They were just caused by the amount of tasks that we were giving to the operator.
Okay.
But there were two kind of main things that led to high workload. So the mission plan generally didn't lead to high workload. You pulled the mission plan and you hit a button and it executed, right? There were two things that led to high workload. Having to create tactics. So I mentioned the live virtual, and we were having communication issues one day. And so the system was going up and down. And so we switched to wanting to deploy the virtual agents. So because the communications kept going up and down and we had live platforms on the launch pad, the operator had to really be careful about which vehicles they were choosing to verify that they were choosing the virtual vehicles over the real vehicles. That led to a lot of workload in that particular day. The other thing that happened is when you launch these huge swarms in these small areas, the vehicles get blocked by one another, and they're autonomously planning a navigation path. But if there's another vehicle near them, then they're blocked. So the operator would do things like trying to nudge them. So with a UAV, the UAV that was nudged would go up like 10 feet and try again. With a ground robot, it'd move forward or backward or maybe rotate, something like that. So these blockages were often another case where the operator was just trying to figure out what's going on with this vehicle. Should I automatically tell it to land? Should I give it a different task? Do I need to give it a different goal point for its task? So those were things where the operator is kind of doing some interactions with the system, and that's typically what we saw. There were a couple of instances on some other days, not the day I presented, where we were having so that day that I mentioned that was 29-mile-an-hour winds, that caused us huge problems with our communication system with the LTE. And we went to launch our vehicles and we're launching things and things aren't happening. And so the operator's trying to figure out, is it communications? Is it the interface? Is it something else, right? And so you can see the workload go up there as he tries to figure out what's going on. And then what was the other one I was thinking of? There was another instance. Oh, when the UAV started falling out of the sky. We had a situation where that's that same day. And we had switched over to a different port for communications in order to be able to just ensure we were working with the simulated vehicles. And we went to switch over to the live vehicles, and it's literally like a 1-minute switch, right? Because we deal with the simulated and real vehicles exactly the same in the interface. And he forgot to change the port. So he issued the mission plan that actually went through, but then he couldn't issue his tactics. And so he's frantically coming out of the headset, trying to change things in the system in order to get onto the appropriate port. Meanwhile, one of our team leads is yelling, UAVs are falling out of the sky, RTL them, like literally yelling at him, right? And he's like, I can't do anything, you gotta wait. So you just totally see the spike in workload at that moment where he's just trying to do so many things. So yeah, there's a lot of different things, but mostly I would say it would be the individual tactic generation. And mostly when they were not having the system select the agents for the tactic for them. The other thing is if you were trying to select an area, so let's say you wanted to set up a surveil that kind of goes from the corner of the building across the street down to the bottom of the street and back around, putting in that area is also a higher workload situation. So there are, the interface has gone through tons of changes over the last 5 years, and there's always things you can think of to do better. But I will tell you, it's way better now than it was 5 years ago.
Thank you.
It was a very informative talk. I really learned a lot, Julie. Thank you very much. I'm wondering whether there is a quantitative evaluation of the difficulty in the decisions of the human. For example, in terms of whether the result of the decision is really something predictable. That would be a very...
If the result of the decision is what, sorry?
Would be predictable, right?
Predictable.
Or really, if it is something completely unpredictable.
So I would say...
Does it correlate? Is there any graph between difficulty and performance? Or
so that would be an interesting thing to do for something other than the DARPA offset data set. The DARPA offset data set, oftentimes the tactics are coming from the team lead and saying, okay, I want you to put a vehicle over here. I want you to explore this area, right? So I would argue there isn't a lot of nuance in the operator's decision-making, as opposed to, except for like that instance we were talking about with the turret and switching vehicles. I think in the other domains, you could look at that. I'd have to think about what you would log to do that, because you'd need to log some things through the system that we don't currently log. Yeah, but that would be an interesting aspect.
Thank you for the great talk. Have you or others looked into maybe modulating the amount of autonomy in the system as a function of the operator's workload, so that perhaps during a time of high stress, you either prioritize to only provide like really high priority items to the...
So that's our goal. And I mentioned the brief study that my student did. That's where we're going. I think, there are people who would argue that they've done that, but I would argue they've done it in very controlled laboratory settings that are not as complex as the type of environments that we work in. So they're using things like cameras or, highly reliable, expensive eye trackers. They're not taking, the kinds of technologies that we're using to do that. And so that changes the problem a bit. There's a question back here.
I was just curious, how many times, so you've done a lot of scenarios, right, on the field. So how many of those were actually successful? So how many of those were you able to go through all these 3 phases and get to the end of the mission, right?
I mentioned earlier, having 3 robots work reliably. Now try to have 200 or 100. It's always a challenge. And you saw on that one slide how many different numbers of robots we had. And the environment is very challenging too. So it's somewhat dependent. In the 3rd exercise, I think it was, the one at Camp Shelby, the picture that I showed you at the beginning where the robot was inside the building and I said that the high value target was on top, that is as close as we got through all 3 phases. And we didn't get the high value target because our UAVs were not, we only had solos then, and solos don't fly indoors. So we couldn't get indoors. After that, we had one field exercise canceled. And then we had another field exercise where it was kind of like he said at Benny, nothing worked. We had just, you sit there and you're like looking at Mount Rainier going, do I need to do a pago to the mountain gods to get this to work? You know, it just was one of those things where every little thing seemed to go wrong and it just kept compiling. So we had a horrible field exercise that time. And then at this last field exercise, they made this scenario exceptionally challenging. And I have some data, I couldn't show it to you, but when you look at the data, you see that the vehicles are neutralized, even the UAVs, at rates that are just astounding. And you could almost not get through phase one because they neutralized so many vehicles. At one point, they were neutralizing our UAVs at 35 meters above the ground. Kind of hard to be successful when your UAVs are getting neutralized at 35 meters above the ground. So, you know, I would argue that probably only that one field exercise, we were super successful. Now, we did succeed in getting robots in the last field, actually in multiple field exercises, not just the last one, into buildings. But, you know, the issue is this technology, the robots themselves are very inexpensive and they aren't really built for the things that they wanted us to do, like getting in those buildings, going up and down stairs. So that's one challenge. And then you've got the sensors that are also a challenge. And, you know, some of the rovers and a few of the UAVs had NVIDIA processors on them. So we had good processors there, but most of the time we're using a Raspberry Pi. So you don't have a lot of capability to do very advanced processing. So I think all those things lead to challenges of being able to successfully complete the mission. Now, having said that, on the final day, actually Tim Chung, who's program manager, told us on Monday that on Thursday, the day after DV Day, that we were going to have both teams on the Cactus deploying simultaneously, which was something that had never been thought of as far as we were concerned. And then on the final day, he wanted every vehicle from both teams up in the air, you know, deployed, and we were trying to deploy 300 vehicles. And it did happen, but that wasn't intended to play the scenario. That was intended to get as big a swarm as possible for Tim. So yeah, definitely interesting challenges. Probably one of the more challenging things I've done, and I've done some pretty challenging things in field work. Yes. Turn your mic on, Francis.
Hear me now?
Yes.
Okay, great. You mentioned a scenario where like, you know, there was a high workload and, you know, the person was getting yelled at because stuff was going wrong, but did you guys try to control sort of external stress from people or anything else in the environment as they try to perform?
That's a very good question. So in prior field exercises, we would allow observers into the control room. And so, you know, the operators would say, oh yeah, the head of DARPA's here. Oh yeah, the head of Futures Command is here or whatever. And that, you know, they talk and they ask questions and things like that. And that creates another level of workload. At this field exercise, we actually tried to contain those kinds of activities in another room on another floor of the building. So it really was just myself, the swarm commander, and then the team lead typically in the room. But that made a big difference. Okay.
So let's thank Julie again. So thank you to everyone for joining us today. As a quick reminder, this and previously recorded talks can be found on our YouTube channel and website. Please tune in on December 2nd. That will be our next Grasp on Robotics talk, and that will be again at 10:30 Eastern Standard Time. Thanks, everyone.